All right, so I decided to make a coffee machine for my design. And my objective was to make the most cost-effective machine that's on the market and the most safest. So I first started with a algorithmic state machine. It first starts at reset as the default state. As soon as the machine is powered on, that's its default. From there, it'll go to a condition to see if the water level is filled up. If it is, it'll go into the next state of saying that it is filled. Then it'll check to see if the machine lid is closed. If it's not, it goes back to reset and turns on an LED. If it is closed, it then starts heating up the water. If the water reaches a certain temperature, it fills into another chamber. If it's not hot enough, it goes back and keeps the water heater on. If the water is hot enough, it checks to see if the machine lid is closed again. If it's not, the LED comes on and goes back to reset. If it is closed, it checks to see if the coffee carafe is inside the machine. If it's not, another LED comes on that says to put the carafe in and goes back to reset. But if the coffee pot is inside the machine, it starts to pump the hot water out of the reservoir and starts brewing the coffee. All the while, it's checking to make sure the machine lid is closed and that the coffee pot is inserted as well. If they are, then it checks to see when the water level inside the hot water reservoir goes below a certain minimum level. Once it reaches the minimum level, the finished LED turns on and a timer starts up. The timer starts at 0 and starts counting up just like a digital clock to tell you how old the coffee is. So next we can produce a state table that has all the different outputs. On here, let me see. Alpha represents the water that you fill in from, just say, tap water. Beta represents the lid sensor. Then lambda represents the temperature sensor. Psi represents the carafe sensor. And delta is the water level sensor inside the hot water reservoir. Then for X, Y, and Z, X is to check to see if the lid is open. That's the LED that turns on. Y is the carafe LED, and Z is saying that it's successfully brewed. So just following through the ASM table or ASM chart, we're able to then fill this out. And then next. These were the expected outputs. As soon as you flip the power switch, the on LED will illuminate. At any time, if you open the lid, the close LED will come on, or if you take the carafe out, the insert pot LED will turn on. And then once it's finished brewing, the green ready LED will illuminate, and then this counter will start counting up. All designs will follow this. Put our hardware in the A star, B star feeds out into D flip-flops and then feed back into A and B, which drive the whole design. Regardless of whatever hardware we put in here, there will be an overhead cost of a crystal oscillator, which costs 55 cents, and a IC chip that has 2 D flip-flops built in, which costs 53 cents. So there will always be an overhead cost of $1.08 for implementing. So my first design was to use logic gates. So using Boolean algebra, because a K-table was, or a K-map was just a little too large for 7 inputs, I used Boolean algebra to simplify the expressions. These are the simplified expressions here. I then used multisim to implement and verify the output is adapted to. The cost of, I decided to use these logic gates as I researched, since they had the lowest cost to their heat tolerance, and also their propagation delay was low enough. So that's why I chose these particular IC chips. And this would be the total cost of this design, which was $7.62, going with logic gates. Oh, and for one of the expressions, it requires a 5-input AND, and no 5-input ANDs exist in IC form. So instead, what I would have to do is use 4 different 4-input ANDs and daisy chain that with 4 different 2-input ANDs to effectively produce a 5-input AND. Next, I considered the 16-to-1 multiplexers. Here I did have to use maps to implement. So here is the massive amounts of K-maps for them. And then the simplified expressions for each input for each 16-to-1 multiplexer from I0 through I15. This is what would be fed into those lines, while next. This is what the 16-to-1 multiplex look like if you were to implement them. And the cost for the multiplexers, since they require additional logic gates, because each input requires some ANDs and ORs to be fed into the I slots, that requires additional cost than just the multiplexers alone, which drives up cost to $20.94, which is nowhere near as efficient as or cost efficient as logic gates alone. And finally, I decided to try PAL. So inside of the device that I went with, the PAL16R6CN, this is what it looks like inside. It's very simple to implement because all I have to use is the simplified Boolean algebra that I had done previously. And each unit only costs $2.65 per PAL. So this is the implementation where the X's represent the connected portions, and the X's and the F represents the fused, which means it's just an open circuit there, so unused. And these are the technical limitations of all the devices. The multiplexers in particular are one of the worst ones to use because the propagation delay is 440 nanoseconds, which is by far the largest propagation delay out of all the devices. And many of the logic IC chips can only withstand temperatures of 70 degrees Celsius. To print or to brew coffee, you have to use around 92 degrees Celsius. So it's really important to have chips that can withstand up to 125 degrees Celsius at least. And that is why I went with the PAL, simply because for one, it's more cost effective and it can withstand higher amounts of temperature, and it has the lowest propagation delay out of all chips and multiplexers. And so that's. Are there any questions? Nope.
Okay, so if there are no questions, maybe I should ask. The very first question that came to my mind, Kenneth, was what are these sensors? I mean, I know that this is really not something that you should have considered or part of this design, but I just want to know if you did do any research for the sake of other people, just to know about, I mean, for example, the temperature sensors, the weight, what are they?
Yeah, I didn't really do too much research. I would assume that for the lid and carafe, both of them would be acting as dead man switches, to where it's just a button that has to be pressed down. And as soon as that button is released, a 0 would come out instead of a 1. So it's always looking for a 1 output for those buttons. Then for the temperature, it's just a, I forget the name of what it is, but it's used in thermostats. It would be a sensor similar to that. And it's
So
just looking, yeah, it's just looking for a certain temperature to be reached, and then a 1 would be outputted for that.
they usually use thermocouple. Is that what?
Yeah, yeah.
Thermocouple, right? Which is just a piece of wire with, obviously inside there are two materials, just one tip with two different materials that conduct heat differently, and that's what called thermocouple. And you obviously, it's calibrated against temperature. Yes, thermocouple. Great, yeah. The reason I brought these questions, because this design again seems to me as absolutely sellable, presentable, and you could offer this to coffee manufacturers brilliantly. So if you went about this by adding the cost of these sensors, how they would be mounted, how they would be powered, because it seems to me that this should work, will work, and it's, why not? It's great. So what would be that if you call advantage of this over the existing coffee maker machines that are on the market?
Most coffee makers today, they don't shut off when you open up the top lid. And if it's nearing the end of the brewing cycle, it can splatter hot water out towards you, which is nearing boiling temperature.
Absolutely.
So this is just much safer for the end user.
Absolutely. Now, this is the point about this design that I'm glad that, well, you obviously had it in mind. I was just hoping that other people grasp that too, because this has two advantages over the existing coffee making machines that they sell in Best Buy maybe, or I don't know, other places. Great, absolutely brilliant, Kenneth. I'm really glad. I really can't see anything wrong with this design. Absolutely none.
Thank you.
I would still like to say that you are too exempt from the final exam for this course, because you have covered every point that we needed to know, so that you know how to design, and you've gone about this brilliantly. Thank you very much.
Thank you.
I just jumped the final conclusion because nobody had any question. I mean, are there any comments, any question about anyone?
Your prices, are these based off of actually buying a thing, like mass producing, or is this just based off like if you bought one chip?
This is one chip. All these prices are simply for one chip.
All right.
I decided to do that obviously the price would come down if you were to buy in bulk. So this is the most expensive that it would ever be.
Oh, okay. That's what was my question, because I was looking at these prices. Like, I know some of these chips are cheap, but if you buy one, you have to pay a lot in shipping and handling. So that was like that's what I was.
Consider shipping and handling. No.
Oh, okay.
It's just the cost of the unit by itself, no shipping and handling. Yeah.
Okay. That was just my question. Thank you.
Yep.
Now that you've answered that question, I just wondered, Kenneth, if you were to make a prototype, if you were to actually manufacture this machine, is that how you would make it? I mean, the way this picture that you show, is that how you would design it?
I would change some things about it, but for the most part, yes.
I like this very much in comparison with those that have a sort of a horizontal panel in front of them. You know how this is
Like
kind of,
in particular, what I would change is the water filling on the back of it. I would have a window to where you can see how much water is inside of it instead of it being solid. I just didn't put much time into modeling it.
right, okay. Well, since you have a sensor there, okay, but that's still good. No, I'm talking about the the coffee machine we have here. It has a panel right in the front of it. It's horizontal, and that often gets dust and coffee, and it gets dirty and it's difficult to maintain. But this seems much neater, much nicer, in my opinion.
Thank you.
Very, very good. Very nice. Your timing was was also very good, actually. 37 to 53. You started at 10:37 and you ended in 10:53, which is very good. Right time.
Yeah.
Great.
Should I stop screen share now?
Please, yes, please.